So it turns out there are quite a different, a bunch of different definitions of versions of vertex algebras, and one sometimes adds some small conditions that make them a little bit nicer, and for most known vertex algebras, these conditions hold. And the one that ensures that the normal ordered product is well behaved is called a grading restricted vertex algebra. So in particular, if you read the works of Huang and others, of E.G. Huang, then he's always working with these types of vertex algebras, because the grading restriction condition makes, in particular, tensor categories constructions quite nice. So this is a vertex algebra as before, but we require that the vertex algebra is graded, integer graded, where these Vn are eigenspaces. We require that the Z2 grading is compatible with the Z grading, in the sense that the integer graded part is even and the not integer graded part is odd, but also that is not necessary. So, but for example, we know that the vertex algebra is grading restricted. So that means the eigenspace vanishes if the eigenvalue becomes too negative. So this.
Do you know something about the degree of this V sub something? I mean, how do you do this computation?
This one here?
Yes.
Well, I can. This is the.
You know something about the commutator?
Yeah. So I can write. So I write this as L0 V2 m minus 3 minus V2 m minus 3 L0, so the commutator, and then I add what I subtracted, and then, so I write this expression, I add a nice 0, so that I have here the commutator. The commutator I know, it has it acts as n2 plus r minus m minus 1. And here I know that V3 has eigenvalue n3. The two add up, and I get this expression. Yeah. Okay, so this means this tells us that so what does this tell us? It tells us that this vector here is in the eigenspace of this eigenvalue. But we know that this eigenspace vanishes if this eigenvalue is too small. So we see that, in fact, and this, of course, we can solve for r. So this means this vanishes if r is less than n plus m plus 1 minus n2 minus n3. But these are all fixed numbers, right? So this means this infinite sum collapses to a sum starting at this bound going up to -1. So this means it's a finite sum, so this is in V. Right? And this nicely illustrates that at least the action of the first element, first summand of the normal ordered product is well defined on a vector. And now let me repeat the computation for the same second summand. Is it okay if I erase this? No. Okay. Okay.
I think maybe it's better just not to repeat the computation and leave it as an exercise.
Yeah. In fact, the computation is almost the same. Sure. Let's do this. That's a.
I mean, now that you had this long discussion, I realize I'm confused about something in this definition of vertex algebra.
Sure.
But why is that bracket well defined at all? When you write z minus w to the n times something, that's something I'm now concerned that it is not well
What are you now exactly?
The locality axiom. There's a commutator sitting here.
Mm-hmm.
And it's a commutator of two things you didn't have a right to multiply.
No, here there's a very big difference. They are not the same variables.
Oh, okay.
Right? And now, a very good comment. Of course, this is totally non-well-defined if z is equal to w, but that's, of course, we know that because the commutator is a sum of delta distributions with coefficients fields, right? So
this is really the purpose of making them having said
yeah. But it's good to point that out. Yeah, let's do the other part as an exercise, and in fact, I could give many small exercises like doing this computation. This one is actually very quick, and you can always ask me about the exercises between the lectures or after lectures if you want. I can also do them with you if you want. Okay, good. Now, the heart of the VOA axioms is the locality, and the locality as defined like this is first of all the way it was first defined, and it's the way you prove that you have a vertex algebra. Now the next thing you do is you try to find equivalent definitions of a vertex algebra, because each definition will hopefully have a good purpose. Right? And it turns out locality can be replaced by two equivalent conditions. One is a Jacobi identity, which I will mention the moment we will also use it. And the other one is called duality. And let me tell you what duality is. So duality is maybe closest to physics.
By the way, are we now, you've given us three increasing set of axioms for the VOA. There's the one maybe before you add Virasoro, then there's the one with also Virasoro, and then there's the one with gradient restricted in addition.
Yeah.
As you proceed further, which are you using and when?
All right. Let's stick with this one, because then. So this one is necessary once we are going to talk about tensor categories. But before that, I will not use it, I think. But yeah, let's stick with this one. That's a good point. Okay. So you saw that the vertex algebras have a lot to do with formal power series, and one thing we talked about is that it was important if I had something like 1 over z minus w, whether I expand this in the region where w is smaller than z or z is smaller than w. And the duality property is concerned with the different expansions of products of fields in different regions. So, and the nice thing is that somehow immediately incorporates a commutativity and an associativity property of the product of fields, which so we would like to compare different spaces of formal power series. So we start with a vector superspace, and now we are looking at the space of, let me first write it down, of polynomials in the variables z inverse, w inverse, and z minus w inverse with coefficients, formal power series in z and w. And now we would like to embed this into three different spaces of larger spaces of formal power series. The first one is a formal Laurent series in one variable, say W, and coefficients formal Laurent series in Z. Right? And always speak it out loud that you see the difference, right? Here it's a formal Laurent series, means it's a power series in W and W inverse, where the pole order of a W inverse is bounded. And the coefficient is a power series in Z, a Laurent series in Z. That means the same thing. The coefficient is a formal power series in Z, where the pole order of Z inverse is bounded, but for a fixed W coefficient. That means it's not globally bounded. That's the difference.
Have you purposely put two parentheses on one side and one parenthesis on the other side?
No, of course not. And here we just interchange the role of the two. And here we look at a Laurent series in Z minus W with coefficients Laurent series in one of the two. And now you have, let me describe these embeddings. So what can we do for the embedding of this space in this here? Let's just think about it. What do we have here? It's polynomials in Z inverse and W inverse with coefficients power series in Z and W. So that's of course all perfectly already in here. We have to do something to the Z minus W inverses in order to get Laurent series of this type. Right? So let's so these are expressions of this type with a property that the overall pole in W is bounded. Right. In particular, we already have that any polynomial in Z inverse and W inverse with coefficients power series in Z and W is already in the space. Right. And now what do we have to do in for powers of Z minus W inverse? Well, we have to expand it in such a way that the pole order of W remains bounded. Right. So this means we use the expansion that this is 1 over Z times 1 plus W over Z plus W over Z squared, etc. We expand in the region where W is less than Z. So this defines F. Of course, H is defined in complete analogy. I just expand in the other direction. And I now, I mean H, I'm sorry, H. And now we have to talk about G. So let's first write down. We are in this case looking at Laurent series in Z minus W, where the coefficients are Laurent series in W. And so in particular, if we look at what we have that any polynomial in Z minus W inverse with coefficients power series in Z and W is already nicely in this space. And we now have to say, what do we do to Z inverse? Well, what can we do? We have to express a Z in terms of W and Z minus W. So we write it as W plus Z minus W. And so that means we write Z inverse as 1 over W plus Z minus W. And then we do a similar expansion of this in the region where Z minus W is smaller than W. All right, because what we need to do is we have to keep the overall pole of Z minus W bounded. Here we only decrease the pole order, so this is perfectly fine. Okay. Okay. So via this 3 embeddings, one can formulate the duality property. And so for all, we fix 3 vectors in our vertex algebra. There exists a power series, let's call it f of v1, v2, v3 in our in the space of on the top. So
V1 and V2, V3 still in the eigenspaces like V n? Or is this just like on the right-hand board?
right, no, that's not important. No, that they don't have to know. There exists such a with a property that we can now evaluate f, g, and h on it.
Font size, please.
Yeah, I think so. Yeah. Yeah. Also, the pens are getting losing their color, right? Yeah. So we apply our 3 embeddings f, g, and h to this function, and now let's think about it. If we act with a field on a vector, we get a Laurent series. So that's a Laurent series in V, and then we act on every coefficient with the next field, so every coefficient becomes a Laurent series again. So this means this expression is in the space of formal Laurent series in W, where the coefficients are Laurent series in Z. And similarly for H, we can just interchange the order of the action of the 2 fields, and we get a corresponding And I just noticed I assume here that V is even. Otherwise, I would have to put here an additional minus sign. Well, why don't I put the minus sign here to have it?
But that's this extra thing you said yesterday, right? That it's a Laurent series.
Yeah.
It's not in the original definition of VOA.
It,
y of v2 comma omega, y of v2 comma w of v3.
yeah, it was not in the definition of a VOA, and but if we now assume that our VOA is grading restricted, then that property holds.
But that's an exercise we still have to do.
Yeah. Mm-hmm. Yeah. And now, how can we possibly get a Laurent series in Z minus W? Well, then our insertion point must be Z minus W, and what you do is here you take the field Y, but now corresponding to the field V1 evaluated in the formal variable Z minus W, acting on the second vector. So it's a convoluted expression. Okay. But here, this expression becomes a Laurent series in Z minus W. Then you can use linearity to pull it out, and then you get the additional action, which gives you a Laurent series in W. And duality, so we say VOA satisfies duality if for any triple of vectors there exists a function f with this property. And
that every VOA satisfies duality because it satisfies locality?
yeah, I'll say that as stated in a moment.
Okay.
So let's first look at this expression. There was a question?
Yeah, I mean, in the first two, you somehow apply V1 to, no, like the order of, like you have V1, V2, V3, the first two. But in the third one, you have V2, V1, V3.
Yeah.
That somehow, that's how it's supposed to work.
Yeah. Yeah, and in particular here, you see these two is definitely a commutativity property because I changed the order of action. And you should think about these two as some kind of associativity property, because what do I do here? I first act with this one on this one, and then with this field on the answer, right? But what do I do? Yeah, and what do I do here? I first act with this field on the second vector, and then the answer, the field corresponding to the answer, acts on the original vector. So you should think about the relation about these two as an associativity property, because you should think about it as having brackets here around, and the relation of these two as a commutativity property. And the statement, the theorem is, that's due to Huang, is that these locality and duality are equivalent. And for that, he requires the VOA to be grading restricted. So yeah. You can replace the locality axiom by duality. So it's and and that's kind of a nice thing. So it's really time for a break. I mean, you always want to generalize, right? And we don't want to talk about VUAs, that's boring. We want to talk about representation theory because that's what becomes interesting. And now, so that means you have to find a notion you can work with, and that generalizes. It turns out, so for locality, we'll have 3 equivalent notions via locality, duality, and the Jacobi identity. And it turns out for modules, all 3 notions nicely generalize, but then for intertwining operators that realize tensor products, only the 2 latter ones nicely generalize. Yes? Hmm?
So this space embeds in those 3 spaces. I think part of the statement of duality is that if you take y of v1, y of v2, v3, that actually lands in this space instead of just being in the bigger one. Because a priori, it doesn't even have to be in v several brackets. It doesn't even have to be in the top thing, right?
Say it again.
So if I just pick a VOA and pick an expression of y v1z, y v2, omega v3, that what space does it live in without looking at, like, before this claim? Like, before this claim, it just lives in v parentheses z parentheses omega.
Well, yeah, so you can, so if you act with a field on a vector, you get a Laurent series always. So that means it depends on the order you evaluate it. So here, this expression is a Laurent series in W. And on each one you act with a field, so it becomes a Laurent series in W, where the coefficients are Laurent series in Z.
Yes, so now the claim is that if a VOA satisfies duality, this expression actually lives in the smaller field of, like, the VZW, smaller that embeds in this bigger thing.
That's the statement of duality.
That's the well, yeah. The statement is there exists an expression in the smaller space, so that if absolutely you're right. Hmm?
Okay.
You can phrase it like this.
Okay.
Somehow even stronger, right? Because you're saying like there exists one for F, for G, and for A, and they're all the same. So it's like
Yeah.
it's not just there's a pre-image; it's like there's one global.
Yeah. Yeah, it's a very general thing.
Okay, thank you.
But
Yeah.
can you formulate the locality again? Because there was an n in this locality, and how is this n related? Is this n now going to be constant?
And the n is so the locality, to recall it. Whoever wants to take a break, please take your break. Locality was that for so let's write down locality for this given 2 vectors. So for this 2 vectors, if I write down the commutator and multiply it by a sufficiently high power of z minus w, and this n depends on these 2 vectors, then it vanishes. Now, where will we see this n here? We will see this in the pole order.
There was an n in the grading restriction.
That's a different n. That's a different n. That's a different one. It's not the same as this one. The n in the grading restriction, the alphabet is too short. This is a different one. Yeah, let's have a break.